yesterday we started talking about hydrates, right? And so we said, okay, these are those funny little things that have the dot in between them. I pulled out a couple of these just to kind of show that I'm not making it up about the dot thing. They just kind of link them up like that. And then usually all these bottles give us some sort of a formula weight. So it kind of takes those things into account for us. Okay. I'll pull those bottles back out in just a second. All right, we came to the conclusion that we can memorize the value for water, 18.02. Yes, that one. Okay, 18.02, and you can kind of just count it as however many waters you have, you multiply it by that number. All right, we also got to see that that number in front of the waters, we're going to count as moles, right? So this is saying 10 moles of water. And so the coefficient looking thing is what tells us that. And then in the name, we use prefixes to do that. So the first couple questions on the lab today are going to consist of you being able to name, okay? Then we got to run through the process of finding the percent composition of water with the formulas, right? And so we first had to find what is the mass of water. So ultimately what we're doing is we're saying, okay, water is 18.02, and I'm going to multiply it by whatever that coefficient value was. And then you get that number. And then we take that divided by the total molar mass. So what we got to see when we broke it down in the next example was that we had to add up everything for zinc sulfate, and then we had to add the water to it to get the total of 287, blah, blah, blah. So then ultimately we took water over total to get a decimal, move that decimal to the right, and we got 43.86% yesterday. Okay. So one thing that I would like you to add to this page is that this process right here, we're calling your theoretical values, or your theoretical way to obtain this percentage. And by that, I mean accepted values, right? Accepted or theoretical. Because in the lab today, what you're going to be doing is you will have a portion where we're going to focus on how to get that percentage now from lab data and from actual numbers that you're measuring, okay? So you can get your percentage that way, and then you can compare it to, if you know what the formula is, you can compare it to what it should have been and see, checked yourself on your lab kind of thing, okay? So this process that we just did right here, this was your accepted value. This is how you get your accepted value for the percentage, okay? Does that make sense, kind of? It's just another word that I'm throwing on your plate. All right, so looking across the page, we have this little portion right here. Let's go ahead and run through these couple questions. Forgot what I was going to say. Oh, look through those two little paragraph things, and then I would like you guys to try to start answering those questions. What is a hydrate versus what does anhydrous mean? So read through some of that description. I don't mind if you work with your lab partners to do that, to get this done, and then we'll kind of check back with each other on that answer, okay? We're good. All right, so we said this was the anhydrous salt, so I hope you at least labeled that on your picture. And then this one was the hydrate, or hydrated, if you want to keep them kind of the same wording. All right, and this one we said was blue. This one was a magenta. I'm going to put magenta again. Thank you for supporting that. All right, so once again, I said this one had to do with when it is the full formula. The blue is when we got rid of the water, and we just talked about that we evaporated off, which involves heat. So ultimately, what is a hydrate?
With water.
With water. Okay, so we could say a compound with water. Okay, and something that I asked this morning was, are these molecular compounds or are they ionic compounds? Good. They are ionic. Okay, we're not really going to be dealing with hydrates with covalent things just because these are crystallized. So they're salts. All right. The generic term for ionic compounds is going to be the word salt. It doesn't mean table salt. Okay. So just because I say that you're dealing with a salt today does not mean go and eat the chemical. Okay. I know. Bummer. All right. So it is an ionic compound with water molecules attached. Okay. I'm sure whatever definition you have, as long as it's in the same realm, is probably fine, so you don't have to rewrite it or anything like that. All right, so if that's what a hydrate is, what does anhydrous mean? Without water. So I'm going to say lacking water. I liked what you said too, though. What did you say?
Without water in the structure.
Yeah, without water in the structure. Perfect. Yep. All right, so lacking water. So I'm going to even give us a very informal way to think about this. We're going to call the hydrate a wet salt versus dry salt. Okay, this is not the answer to number 3, by the way. Okay, so we're going to, on the other side, when we get to the calculations, we're going to be labeling our hydrates as wet, and we're going to label our anhydrates as dry. Okay? If I can spell this word and get through this question. There we go. All right. Okay, so anhydrate. So wet salt versus dry salt. Now, when I'm saying wet salt, I would like to make this very clear. This is a wet salt. Okay? It does not mean that there is water, little droplets on it. It is literally, like you can pick it up, it is solid. Okay? So it is not, I just want to make sure that we are clear as I'm saying that in your calculation. The wet stuff and the dry stuff, it's not that it's wet and dry as we probably know it. It's the fact that the water molecules are with it and they're not. Are we good with that clarification? Yeah? Perfect. All right. Because the last thing I want is you guys picturing, oh, there should be a puddle of water there. No. All right. So why must the mass of the anhydrous salt be measured immediately upon cooling? So we know we're going to have to heat it up to get the water out of it. So why is it important to not leave it uncovered in the classroom and leave it just in the classroom for a while?
It'll absorb more water.
It'll absorb more water. There's such thing as humidity. Anybody with hair suffering right now? We all know the struggle, right? So humidity in the air, it means that salt is going to reabsorb all that water that's sitting in the air right now. All right, cool. So that's going to be my one-worded answer. All right, flip the page over. Okay. So what I'm going to have us run through as quick as possible, I'm hoping 10 minutes or less. It's going to involve you guys needing to walk me through the calculation, okay? We got it? So make sure your thinking caps are on. Make sure you are drawing all the pictures. I know it looks silly and it feels silly to draw pictures, but I will not answer questions if you don't come to me with your paper with pictures drawn on it. I just won't. I'll say, okay, go figure it out then. So this is our data that we're going to be using for this example, okay? So what I have here, it says the first step was that we had to weigh the mass of an empty crucible and cover. What the hey is a crucible and a cover? Anybody know?
The crucible is it's really warm.
Yeah.
It heats stuff up really hot.
Yeah. Good. It's something that you can use with metals, I believe, molten metals and stuff. Ours is not huge. Ours looks like a little, what are those called? Thimbles? Like a thimble? I don't know. Anyway, ours is like super miniature. This is actually a crucible, all right? And then here's the little lovely lid that goes on top of it. It's so tiny. Isn't it so cute? Like, so cute. All right, so crucible and cover. So we're going to simplify, and just so you know, evaporating dish is the way that I usually run this lab, and it's just a wider dish that does not have a cover, all right? So we're going to simplify that, huh? Probably not. This has a different kind of material, so those will break a little bit easier, I think. All right, so empty crucible and cover. So what we're going to do is we're going to label this as A. A is the container. Okay? I totally meant to write a line from the number so that you know where it is to A, which is the container. All right. Okay, so letter A is going to be the container. So the way that we're going to draw that, we're going to put A up here. I'm going to have, there's my container. Did it. Done. All right. So mass of the crucible, so the second thing that we're measuring is mass of the crucible cover and the hydrate. So now this second number shows the container plus wet salt, right? I mean, that's what the hydrate is. It's the one that has the water molecules with it, right? So we're going to say container plus wet salt. So let's go ahead and draw what that image would look like. So we're going to have our container plus the salt, and we're going to make it wet by coloring it in. Okay? There's my wet salt. Okay? I'm going to go ahead and label my pictures too so that when I try to figure out the next part, I know what I'm looking at. Okay. Okay. Then the third thing we measure is the mass of the crucible cover, so the container, and the anhydrate. So container plus, what are we going to put? Yep. So the informal to help us out is dry salt. Good. Okay. So letter C, we have our container with the salt, and now it's dry. Okay. So to put the technical terms or the actual vocab words up here, this is your hydrate. This is the anhydrate. Okay. Just to kind of assist you when you're getting to those calculations. All right. So this last thing, so it looks like we have almost another measurement, right? Okay, it says mass of the crucible cover anhydrate after second or third heating. Did that number change?
No.
Okay, why did we heat it up a second and third time?
Just to be safe.
Just to be safe, just to make sure all the water got out, right? So if it had changed, which would be your ultimate number to use? The lowest number. The lowest that it gets, right? So the fact that it didn't change tells me, you know what? We don't really need this one. I would not scribble it out, just lightly cross it out. That way you're not paying attention to that number at all in this calculation. All right, so our first thing that we need to do in order to get to our percent composition, right? Actually, you know what? Even better, I'm going to have you guys do one thing different from this morning. Okay, from these pictures, ultimately, how am I going to figure out my percentage of water? Okay, maybe not from the pictures. What about, what is percent hydrate? What is the formula, the main formula for it? Not dealing with molar masses, nothing like that. Just what is it technically? It's part over whole, so what's the part? Water. Divided by? Total mass. So what would the total mass, what would be the word that would we use the anhydrate or the hydrate part? The hydrate. Good. So the total mass of that times 100, right? It's still going to be water divided by hydrate. So we know, we got to know this mass, and we got to know we don't have a picture to represent water, but hopefully you're already thinking, is there a way for us to calculate how much water left the scene? Yeah, heck yeah, right? It's the difference between wet and dry, right? If your clothes are lighter when they come out of the dryer than when you put them in, that means that it lost the water, right? It's common sense. You guys already know that. Okay, so keep that in mind. It's not complicated. All right, let's go to these calculations. Let's go ahead and write out what we're actually doing. So calculate the mass of the anhydrous magnesium sulfate. So anhydrous means which one? Dry salt. Good. So we're trying to figure out how would I calculate dry salt from my pictures and from the data. You can say A, B, or C, subtracting something, adding something. What do you think? How do I know only the mass of the dry salt? C minus A. Tell us why.
Because you're trying to get just the anhydrate, so you need the mass of the crucible powder.
Perfect. Yep. So we're going to take the container. Sorry. We're going to take the dry minus container. Right? That makes sense. Okay. The example that I showed last period, if that is like, if you're like, what? This is the example I showed them last period. Okay. I have a crucible. There's my crucible. That crucible, it weighs 2 grams. Everybody has 2 grams in your head? We're good? All right. I put a paper clip in there. Now it weighs 3. How much was the paper clip?
1.
Exactly. And you did that in your head, right? Because you're like, oh, the difference between the two, right? We got it. All right. So whatever the change is. Okay. So we have our dry minus container. So go ahead. Let's plug those numbers in real fast. Okay. C minus A. We have 45.56 minus A, 44.36. What do we get? Plug it in. 1.2. Good. Okay, we're going to be using that number. Step B, it says calculate the moles of anhydrous magnesium sulfate. So we didn't have to do this last time, right? We didn't have to sit there and convert to moles necessarily. Yes, we did. No, we didn't. We had to figure out mass, right? We went from moles to mass. So now we're looking at calculate the number of moles. So if I have 1.2 grams, how am I going to convert that to moles?
Isn't it just like avocado's number times 1.2?
Avogadro's number can only be used for particles. So that would be more if I wanted to know the number of atoms.
Oh, okay.
You're not totally in left field though. Like he's on the right idea. It's something that we were working with. So what would be the other option? If it's not Avogadro's number, it's molar mass, right? So are we going to divide it or are we going to multiply the molar mass? Divide. How'd you know? Say that again. So you basically, you went ahead and did your little, bring your word down to the right, and you had mole up here. So you said 1 mole, and then you knew that molar mass goes down here. Yeah. Okay, exactly. So dimensional analysis is what tells you that ultimately you're dividing. You're dividing by the molar mass. So look at what I made you guys. Oh, did I ask you guys to get that number? I did, right? Good deal. What was our number? 120.367. Perfect. All right, we already did that work. So 120.367. We got that from adding a magnesium, a sulfur, and 4 oxygens together, right? Okay, so we got our molar mass of that. So divide those two. What is the answer that you are getting? Should be 0 point something. I think 0, 0.
9.96 e negative 3.
Good. So that would be 0.0096. What was after your 9.6?
That was a 9. Sorry, that's supposed to be right. Yeah, 9.7. If we're rounding.
Should it be 9.96? Sorry, I just wrote 9.6.
Yeah, 9.9.
There he is. Okay. 9.9.
6, but there's a 9 after that.
So we rounded. Got it. Now I understand. Okay, we're good. All right, cool. That works for me. So there's our moles of anhydrous magnesium sulfate. So this is like that. Okay, so just label it for now. Let's go to the next portion. The next part says calculate the mass of water driven off from the hydrate. So A came from our data table. C is also going to come from our data table. So we need to figure out how much water left the scene. So what are the two that we're going to subtract this time? B minus C, and that is absolutely correct. Because what that means, right, is wet minus dry is water. The difference between wet and dry is water, right? Okay, so let's get those two numbers in. So I have 46.79. I'm going to subtract the dry 45.56. So you should be getting 1.23. Yeah? Okay. 1.23 grams. Okay? All right, so now that I have that, the next step is saying calculate the number of moles of water. Okay, so we're going to start with our 1.23 grams of water. We don't have to, I could show the dimensional analysis, but we technically already know how we're going from moles to grams, right? You're dividing molar mass. So here, we can go ahead and go from moles to grams by, I'm so sorry, grams to moles. That was a brutal mistake. Okay, so grams to moles by dividing by the molar mass. So the molar mass of water would be that 18.02 grams. So when we divide that, you should be getting 0.0, I forgot the rest. I think it's 6 something.
Yeah, 0.0683. Take a rounding from there.
Let's go 1, 2, 3, 1, 2, 3, 4, 5. Go to 5 digits. So 0.
So 0.06826.
6? Okay. All right.
Take a rounding.
Yep, that works for me. All right, and that's for water. All right, so we get to stop at that point right there, okay? There is more to this. I'm not going to try to get you through the whole thing today because I want you guys to knock out the Schoology part of this lab, all right? Because you don't actually have to do this bottom part in the Schoology part of the lab. This is what you guys would be expected to do. And so we can kind of table that for now. What you got from what we wrote right here that's going to be useful to you is A and C, because you guys are going to be using data that you get from a video, which I don't mind playing on the screen so that you guys can just get your data and put it in to get those couple calculations. Otherwise, the rest of it just walks you through it, okay? All right, so I'm going to go ahead and stop this little recording.